I'm here to talk about day two operations in Kubernetes, and specifically managing third-party software when you're running it in your Kubernetes cluster. First, a little bit about me. My name is Mark. I'm the founder and CTO of a company called Replicated. We have a platform that enables SaaS companies to ship on-prem installable versions, modern on-prem installable versions of their application, which often just means in a private VPC. And these are often Kubernetes applications. It's a SaaS provider who's packaging their software up and running it inside their largest enterprise environment. Kubernetes, again, we think about this problem on a regular basis. Like how do we make it easy to install? That's important, but how do we make it easy to operate over the long term? Some of our customers who package their software up in Replicated, and a lot of this, like I mentioned, is Kubernetes applications today. So what we've done is we've created an open source application called Ship. And Ship works outside of our ecosystem of products that we're actually distributing. And you can use it just to deploy a Helm Chart or any other third-party software today. And I'm just going to talk about that. I'm going to really talk about the open source world, how you can use it to deploy Helm Charts using Helm Charts, but it's a better way to deploy Helm Charts. Talk about like why that's a better way to deploy Helm Charts, and end with a demo of it. Ship was inspired originally by Brian Grant's white paper. If anybody's ever read this before, it's a great paper. It's in one of the Kubernetes repos, and it's called Declarative Application Management in Kubernetes. And he talks about a lot of his experiences and Google's experiences with different types of configuration management, from templating to inheritance to patching to all the different methods and what worked and what didn't work and why they worked and the various methods they like where they excelled and where they didn't excel. It's a great, relatively short paper, but a really good read on if you're interested in application config management. And specifically, I'm talking about OTS software, off-the-shelf software or third-party software, whatever you want to call it. And the differences that's needed deploying that than deploying your first-party software. So most of us are deploying software to Kubernetes. I didn't see the hands earlier when we asked who was running Kubernetes in production. But most of us have Kubernetes at least in test. That's probably why we're here. And deploying software, we'll build a pipeline and we have tools to do it. But deploying third-party software requires a different set of tools, not the same set of tools that we've been using. The same workflow should work, but we'll need different tools. And the reason for that ultimately comes down to the software packager can't imagine all possible environments you want to run it in. Like when you're writing your own code and going to deploy it to your own cluster, you know the environment of all the different servers and clusters and regions and everything you're going to deploy that into. It may be one, it may be 100, but you know what those are. When you're writing software and packaging it for somebody else to install, it might not even be on true Kubernetes. It may be on OpenShift or some other cluster on some bare metal or something that you haven't even tested it on before that has a different set of needs. And so you need to think about what those requirements are in order to install it. Taking a step back and thinking like, what is third-party software, to kind of give a better definition of this? It's really any software your team didn't write. And that can be anything big like, Prometheus or Jaeger or something like this that's really specific to Kubernetes, or it can be something as small as an agent. Maybe you're running Papertrail and you have an agent, or Datadog or something like this, and you have just a small agent deployed as a daemon set in your Kubernetes cluster, or Postgres or Elasticsearch, or any piece of software, small, large, distributed, single container that you didn't write, and you need to deploy it into your own cluster. So some examples of third-party software that we may be running: Istio, Consul, NSQ, Rabbit, things like this. There's a lot. They require configuration. All applications require configuration. Any software that's packaged requires configuration, from like a deb and RPM to an NPM package to a Kubernetes application. They all require config. I want to think about config here in terms of like application config and runtime config. When thinking about how software is deployed to Kubernetes, there's a difference here. They're configured in the same place, right? We're going to all write a Kubernetes YAML, a manifest, or a lot of manifests that control all of this. We put config maps and environment variables and ingress controllers and replica counts all in the same files, but they're different. One is a finite set that the application packager knows what they are. If I'm packaging Postgres supports a lot of environment variables, but there's a limit to what they are. I can't, as a cluster operator, just make up a new environment variable, pass it into my Postgres container, and change the behavior of Postgres by doing that. No, Postgres has a set that it knows how to do, and the config map knows what it can do. Versus the runtime config, there's an unlimited combination of sets that are available once you include custom resource definitions, operators, and Kubernetes extensions that are in there. The application packager doesn't necessarily have to understand what ingress controller I want, what storage class I want for my stateful sets, or how I want the rolling update strategy to be deployed. That's cluster level config. That's not application level config. We configure this today. Often, there's a lot of different tools that do it. Most of them use templating. Most of them is Helm. Most of us use Helm to deploy third-party software today. We'll do a Helm install and a Helm update. Templating is good for some problems. Application config, not great for some problems. Unlimited config in a runtime. Helm is actually a great way to prototype an application. It's really easy to do a Helm install of something that you're unfamiliar with, get it running as a prototype, a proof of concept, validate that the application is going to work. But many Helm charts, when we actually get down to running it into a production, don't have all of the necessary config that we need in order to run it inside our own clusters. The ideal configuration for a Helm chart is that the chart maintainer writes the chart and templates out a bunch of Kubernetes YAML. That includes all of the application config and some of the runtime config. Most Helm charts support, templating out the pull policy or an image or pod labels and things like this, but they don't. There's stuff that is in the Kubernetes API that's not templated into the Helm chart, and you don't have access to that. So the ideal config is that you'll run all these Helm charts in production, and somebody else is maintaining all of those, like the chart maintainer is, and you're maintaining just these small values YAMLs for every single one of them. And anytime the chart gets updated, you can take your values and apply it to that and get an updated version of it, and that's how you update to the latest version. That's how Helm works. But because most of the time we need some extended config that's not in a Helm chart, we have to end up having to fork or copy the Helm chart into our own repo in order to make changes to the underlying chart. That way our values, or we can hard code it, or whatever we want to do. Why? Well, because again, like the runtime config is different for all of our environments. Like GKE is very different than AWS, from bare metal, from DigitalOcean, from OpenShift to Red Hat, anything. My storage is different than your ingress, and like all these different configs. Thinking a little bit more about the difference between application config and runtime config, it's really just comes down to app config is a known finite set of config options that the software packager can code for, that they can template, that works really well in a templated world, whereas runtime config doesn't. The options are just independent. The cluster operator needs to make these decisions. Cluster operator often doesn't have the flexibility to make the decisions that, like, these are set in the way that the cluster is provisioned. It's an AWS cluster, it's an EKS cluster versus a GKE cluster, and so therefore the storage class has to be different. Thinking again back to the ideal configuration here, what we end up with once we forked all the charts is, in the real world, the configuration is, I now have all of the YAML under my management. So instead of me having just a values YAML, in order for me to delete a pod label from this, hypothetical scenario here, and then also add in a pod security context and update strategy, a sealed secret as an operator or a CRD, I have to fork this Helm chart, and now the entire Helm chart is in my repo, and I have to maintain that Helm chart. I'm no longer relying on the upstream directly. Then every time that they ship an update down, those updates are spread throughout the entire Helm chart. I mean, sometimes maybe it's just an image update, but often the updates come and they have YAML, stateful stats, everything's changed around, and I have to pull that down in, and I have to reapply all of my changes into that fork, from my fork back into that merge. So in reality, what the cluster operator has is a lot of YAML under management versus just a lot of little values. That was what the intent was down here, just a little bit of values YAML under management, but in reality you end up with all of the manifests themselves. And then forking, when that update comes down, there's a very manual reconciliation process that happens. I forked the Helm chart, I've added in 3, 5, 7 different changes that I need to make to it, and then the Helm chart version 1.1 comes out, an updated version. I pull that down, I have to go find all of mine changes, figure out how they fit into this new one, which is Go templated Kubernetes YAML, so it's a little bit hard to look at to begin with, but I have to go reapply all those changes into it, and then repeat this across 200 apps, plus apps for many Kubernetes clusters across every organization that's running Kubernetes, and it's a pain. It becomes a very manual process, and manual processes are problems, right? Because if this is a manual process and it's tedious and it takes a lot of work, it's not going to be the thing that you're going to do on a regular basis. It's not automated. So you're going to end up not updating that application as often as you'd like to. You'll say, we'll do it when we need to, we'll do it later. Like you're just not keeping it updated at the same cadence. You're keeping your own applications updated. So the goal should be to get back to those upstream Helm charts directly. Like how can we get, so we're not running forks of Helm charts, and how can we go back to just using the Helm chart, but maintain all of our custom config and anything that we need to, whether or not it's supported in the Helm chart. One option would be just to make pull requests back into the Helm chart with all the changes that we want. So if the chart doesn't support an update strategy that you need because it wasn't templated in, you can make a pull request back into the Helm chart. They'll hopefully accept it, and now it is, and you're back on the upstream. You don't have to be on a fork anymore. An example here, just took a quick look. This is a few months old. We looked at the Prometheus Helm chart, and it was 2 years as a stable Helm chart, and it averaged about 1 update a week during that time. So 129 commits, and 100 of those were just to make this thing configurable inside the Helm chart. They weren't updates to Prometheus. They were just add this custom case. It might be common, it might be an edge case, it might be a corner case, just something to make it more configurable for somebody else's environment. The values YAML, which is the context that's applied to rendering out a Helm chart, started with 415 lines. And at the end of 2 years, it had over 1,100 lines, and it's continued to grow. So that's just more complexity, more configuration that you and I probably don't need, but somebody needed in order to run it. We have to think, it does make sense to contribute back and make changes to the upstream Helm chart, but not all the time. Like if it's a thing that's really specific to my environment, I probably don't need to contribute that back to the Helm chart and just increase complexity for everybody else and make it something that somebody else has to take on and learn just so that I can use the upstream. There's definitely common functionality that may be used, maybe it's if something that's good can be used by 80% of different cluster operators or environments, or there's common use case for it, make a pull request back in. It's definitely really good, especially if it's application level config. Once it gets down into runtime config or Kubernetes API specifically, it's not an ideal use of Helm charts in templating. Helm has these functions that can be called, and one of them is toYAML, which literally just takes YAML from the values YAML file and copies it into the templated Helm chart directly as is. You have to control the indentation of it and everything. It's just a sign that that's a kind of a leaky abstraction there between a templating language when really it just becomes a YAML copying tool. And so we've created replicated ship to help solve this problem. It's completely compatible with Helm charts today. Helm charts are a great source of upstream third-party software, but it makes it so you never have to fork a Helm chart, but you keep all of your custom config. And it works with all existing workflows, and we thought about the whole workflow, more than just installation of the chart. We want to also think about how are you going to update it and how are you going to watch for updates and create an automatically merging thing. It's open source today. It's been out for a while. So Ship is an open source tool that's designed to reduce the operational overhead of maintaining third-party software in Kubernetes. And it's all possible because of Kustomize. How many people have heard of Kustomize? Cool, great. So Kustomize is written by Google and open sourced as a Kubernetes SIG, and it uses patching instead of templating in order to provide the same functionality. So you can extend a Kubernetes YAML by writing patches that can add, delete, and change the base YAML, but you keep the patches separately, so you keep them in separate locations. When Kustomize was released, they put it out there on the GitHub repo with here's some instructions on the README, and they had 1, 2, 3, 4, 5, and 5 was interesting. It was optionally capture changes from upstream. And this allows you to periodically rebase your base to merge in the upstream changes. This is really interesting when we saw it because we were this actually solves the problem of third-party software. You don't have any git merge conflicts anymore. There's literally no way you can have a git merge conflict because the base and your patches are kept in totally separate places. They're never merged using git anymore. They're YAML merged, but they're not git merged anymore. We liked it. We made a website for Kustomize.io. So Kustomize.io is a good place. We didn't write the project. It's a Google project, but anyway. So this creates a git merge conflict-free process and allows you to patch instead of forking. Going all the way back to this ideal configuration where the Helm chart maintainer ships the chart and they say, look, this is all the application config, and here's the part of the runtime config that's common. 80% of people need to be able to modify this or some large number. Now with Ship and Kustomize, you can make patches to make all of the changes where you can remove that pod label or add that, like do all the same stuff you had to do before by forking the chart. Now you can just make patches to do all this, and you don't take the entire YAML under management in order to do this. You can only create just the patch. But you have access to the full Kubernetes API. You can modify anything. If 1.14 ships with a new resource, but the Helm chart doesn't support it yet, you can still get access to it. If you want to use an operator or a CRD to replace something that's in there, you can have a patch that deletes a secret and replaces it with something else. If you want to use Vault, you can patch init containers into everything in order to like load secrets in. And it's all customized, and then ship just like automates the workflow. So then what you end up with is you started off with Helm chart version 1, and you have your patch. And then Helm chart ships an update, and ship will pull it down and then use customize to reapply your same patch to it. And no matter how those changes were applied, customize knows how to traverse the Kubernetes YAML and find that. It uses the GVK so it can find it. It's not like a line number. It's not a Git style thing. It actually understands how to read Kubernetes and says, oh, you want a stateful set with this name, go find this port, and you want to change it to that port or something like that. And so your patches can keep applying all the way down. So the reality with Helm forks was that you ended up with all of this YAML that you have to take under it. Reality with ship patches, you end up with still just these little patches that you have to maintain, only the parts that you changed. So instead of assuming 10,000 lines of a Prometheus Helm chart just because you wanted to change 5 things, you might only have a dozen lines of YAML that you have to maintain now. So going all the way back to a workflow, if we think, how do we deploy software to our Kubernetes cluster today? Hopefully something like this. This is a really high-level view of it, but this is probably how we're deploying it. Somebody writes some config, some YAML, you make a pull request into a Git repo, it gets reviewed by somebody else on the team, it gets merged in, an automated process picks it up and deploys it to the Kubernetes cluster. And that's how we're deploying software like our APIs and our websites and everything that we're writing. With ship, the upstream, not your control, like the Prometheus team, the Jaeger team updates their application. Ship detects that, merges the patches in, and makes a pull request into a repo again. So your team can look at that to see what the difference is, merge it in, and the existing workflow can pick that up. So if you have a workflow that deploys your own software to Kubernetes, with ship, you can use that exact same workflow. It doesn't really matter what it is to deploy third-party software to Kubernetes. Thinking kind of what the steps of third-party software is, what's the life cycle of it? There's 3 different steps that ship supports. And if we think about how we actually get third-party software on, the first part is we have to go through the initial config. And we're going to iterate on that a little bit. We're going to find the software that we want, create the config, test it out, work through it, get it to the point where we're happy with that deployment, and then deploy it. And now what we want to do is turn that into an automated process. And we want to watch for any updates to it. And as soon as there's an update available, update our application and then deploy it, and then go back to watching for the next update. And so we don't have to spend any time on that anymore. Ship has 3 modes, 3 subcommands. It's ship init, ship watch, and ship update that can be used in a CI process in order to do exactly that workflow. So I'm going to do a demo. I'm going to take a Helm install with some custom requirements using ship. We'll see how that goes. So I'm going to use console from HashiCorp. Are we familiar with console? Everybody familiar with console? Cool. I will use a large font. So I'm going to just make a new directory to do this. Console has a Helm chart. They ship it. It's their own Helm chart. They maintain it. It's not in the Helm charts repo right now. And they have all of the different values that they can configure. And they have some instructions on how to customize it, and at the end, they actually say use customizer ship if you want to provide some advanced customization. So we're going to just customize their Helm chart. I'm just going to grab the URL to their Helm chart itself. It does not have any first-class support for ship inside it. It's just a standard Helm chart. And I have ship installed. And so ship has 3 modes, init, watch, and update. And we'll talk about the unfork thing in a minute. So ship init, and I'll just put in a URL. It can be a URL to a Helm chart. It can be a URL to Kubernetes YAML. It doesn't have to be a Helm chart. It can be on GitHub. It can be anywhere. As long as your machine has access to clone or use HTTP to download that resource, it will use it. So when I run that ship, I'm in the initial config mode here. And so it downloads it, it detects that it's a Helm chart, and it generates a default, what we call a default lifecycle. Means I'm going to help you go through what the process is to configure this. And it asks it to open a browser. Everything can be run in headless mode. We actually made a decision when we built Ship that the first iteration that you want to go through when you want to first install and configure a piece of software, you probably want to use a UI because it's a very manual process. Automation is really important, and you can run this in headless mode, and we default to everything being automated after you get the initial config done. But we actually built a UI around how to get the initial config done, and we'll walk through that right now. And this is all in the open source Ship application. The first thing it does is it's like an intro screen that tells you here's what it's going to do. It's console, and we're going to set the custom values. We'll go get started. This shows the values YAML that we're going to use to this Helm chart. So this is the context that's used to deploy the Helm chart. And Ship doesn't require Helm or Tiller to actually be installed in the cluster. We actually run Helm template to generate Kubernetes YAML, and then you can just deploy the Kubernetes YAML directly to the cluster. So that's all handled automatically in here. So you don't have to install Tiller. Tiller is going away at some point, but right now, you don't have to have it right now with Helm version 2. I'm not going to make any changes to this, but I can make any changes I wanted to that are supported configuration changes. I can change, the namespace here. Maybe I'm going to change it from running in the default namespace to running in a console namespace, and continue. And what this does now is runs Helm template, and Ship has taken that context, applied it to the templated Kubernetes YAML that HashiCorp shipped with the the console chart, and generated all of the deployable Kubernetes YAML. So now we have Kubernetes manifests. There's a check. And now we're going to go look at them. They're all listed as base. In customized, base in patches are maintained as separate directories. So what HashiCorp shipped is console, that's now the base. I don't have any patches yet. This is still just the plain vanilla Helm chart ready to go. But I can click on them and look at them. I can look at the stateful set here that they ship. And I'm going to make some changes to it. And I don't know what changes you might need to make or what I might need to make, but I'm just going to make a few just arbitrary changes to this Helm chart to show how Ship works. I'll change this 10 gig storage because I need a lot of storage for my console. And I'm going to change it to 100 gigabytes. And so what this did was this used customize to create a patch based on the line that I clicked on. And it created the patch on the right, which is the minimal-ish amount of YAML that can be used to match that originally from the original upstream. So it has the GVK, which is the group, the version, and the kind of the Kubernetes YAML. So it has API version, kind, and then metadata name. And then the rest of it just matches the tree from the base YAML. So it says, once we found this base YAML, go find the spec, the volume claim templates, find the one with this metadata name. Again, customized knows Kubernetes, so it knows that here's how to find a volume claim template. Go find the metadata name that matches the one that I care about. And then go change this request storage to 100 gigs. I'm going to make another change in here too. Let's change the termination grace period seconds. Maybe I know that my environment is weird and I need it to be 20 instead of 10. So I'll click on this, and it appended that to that patch. It created another patch on top and merged those together. And we'll say 20, and we'll save it. So here on the left, we still have the unchanged base YAML. On the right, we have my patches. I can show a diff, which shows what my patch will look like merged in. And you can see if I scroll down that it's changing the termination grace period seconds from 10 to 20 and the storage from 10 to 100. And you can see down here, my overlay is kept separately from the actual Kubernetes YAML itself. I can make any changes I want to. Maybe I want to come into this daemon set here and change, I don't know what I want to change. I will change, we're going to change the image name from console to, some big bank console, because I have a security team that did a review of what this is. And so this should show that's changed. I can continue to make any changes I want to. We'll get past this step now. And now it says it's ready to deploy, and I can continue. It says we're all done. We look here, and it finished for me. I'm just going to open this in an editor so we can look at what it actually created, and we'll make it a decent font. This made a rendered YAML, which is all of the Kubernetes YAML in the console Helm chart ready to go. And it has the 100 gigabytes. It has some big bank. It has my custom image. So this is the merged together YAML with the patches applied to the base, but it kept the directory structure really plain. On the left here, we have two directories. We have base in overlays. The stateful set in base is still at 10 gigs, and that's the original upstream. No changes made. That way, anytime that HashiCorp ships a new update to this Helm chart, we can just pull it down and re-render out this base without any problem. There's never any of our custom data applied to it. And overlays has just those small patches. So I'm only actually have to maintain just these two files, just these two pieces of YAML that I've written that are specific to my changes. And then the other two modes of ship, I can run ship watch. This is going to be a little bit boring, but ship watch will go periodically check that upstream, apply the custom values that I have to it, re-render it out, calculate a stable SHA, compare it to the last version that it had, and determine if the Helm chart has changed. If any parts of the Helm chart have changed that I care about, that my values would include rendering. In this case, it hasn't because they didn't ship an updated version of the Helm chart in the past 5 minutes. But when it does, all ship watch does is exit with a status code of 0. So it's a good building block to hook into CI process, and you can run ship update afterwards. So a really good pattern is to run ship watch and ship update. So when one exits, the next one starts. Ship update will by default run in headless mode. And what this does is downloads the latest version, deletes the base directory from my machine, and then takes my patches and reapplies to it. So in this demo, this would have just created the exact same rendered YAML, but if console was updated, this would have updated my version of console but kept the 3 changes that I had applied into it. So what's next? If you have Helm charts today and you forked them, I encourage you to go unfork them. We realized once we had this functionality, one really cool migration thing that we could do was make a ship unfork command. So if you run ship unfork, and you give it the URL to your GitHub repo that has a fork of a Helm chart and what the upstream Helm chart is, it will actually go and compare them and render them out and then find the differences and back them out as patches so that you can delete your fork and then now have them all stored as an overlay and ready to go. And so you can actually go back to the upstream directly. We host a version of ship on our website. We don't actually charge for it. It's just there as a good demo and you can use it. It has a couple other pieces of functionality that the ship open source thing doesn't have, one of them being that it will automatically make a pull request into a Git repo for you when there's an update. You could build that yourself with ship watch and ship update really easily. We have an operator that does this. We just haven't open sourced that yet, but we will. And we can take the version that we host that has everything ready to go, running as a Kubernetes application and run it inside somebody else's environment as ship enterprise, because that's what we do is we run third-party software in Kubernetes. So the 3 versions of ship open source, which is ship and ship operator. Ship cloud, the free version. I'll actually show that really quick here. If I were to come into here and say, install a new application, and good, I still have that in the clipboard, I can just pick the HashiCorp console chart, click next. I won't go through this whole thing again, but this is just in the hosted version. We're running all the infrastructure for you. You can go through it, and when it's done, it'll ask you to, I won't make any patches here just to get through to the final screen. And this finishes, and this runs the exact same version of ship that we were just running, except now I can actually configure an integration and tell it I want a pull request every time this is updated into a GitHub repo, or I just download the YAML, and then we'll run the watch inside a Kubernetes cluster for you. And anytime that gets updated, we'll reapply everything and make an updated pull request in. Some Helm charts get updated very regularly. And the last part is, for people who don't know how much third-party software you have, we actually wrote another little tool called clusterscope.io. And you don't have to install anything in your cluster. It just comes with a kubectl command. You run it. It goes in, it looks at all the pods and uses JQ to extract all the image names that you have, and you can paste it in, and it actually goes in, it checks Docker Hub or Quay or wherever the registry is that you have and determines how old those versions are, and will just tell you whether you're running updated, whether you have stuff that's out of date or not. And it's really just a tool to help you realize what you have that could benefit from being updated.